We're going to talk a little bit about parameters and statistics. And we're going to introduce two statistical concepts, the idea of estimation and the idea of hypothesis testing. I found this slide when I was a student. I didn't understand it at first. I don't even know what language it's in. But I realized that this slide tells you everything you need to know about how statistics works. You have this population of elements here. And again, it might be the population of HIV positive Hispanic men living in Washington, D.C. That's the population that you want to make a statement about. And there's a number that describes elements of that population. That number is the parameter. So it could be the mean height. It could be the mean number of cigarettes smoked per day. It could be whether they're left-handed or right-handed. There's some potentially knowable number that's a fixed real thing. That's the parameter that describes that population. But what we do in statistics is we take a subset of that population, and that's called the sample. And the number that describes our sample is called a statistic. Now, why do we take samples? Why don't we just get the whole population? Well, first of all, it could be a real pain to try to get the whole population. It might be hard to do that. That's called a census. There are hard to reach elements of the population. But most importantly, once you have a good sense of what's going on in a sample, every additional piece of information you get from the population is worth less and less. If you had 90% of the population in your sample, those other 10 people are not really going to move that number that much. So we think about this idea of we have a sample, which we say with our sample size of n. Now, what we're going to do next is we're going to think about how do statistics behave. And what we do there is we play some thought experiments and we say, let's assume that we actually knew what a parameter was. Most of the time we don't. That's the whole point of the study. We take a sample, calculate a statistic, and say, what does that tell us about the population? What does this little snippet tell us about where the truth is? But in order for us really to understand that process, first we need to go the other direction. Let's say that there's a situation where we actually know the truth. What would we get if we took a random sample, or 100 random samples, or an infinite number of random samples? And that will give us a little sense of how these statistics behave. Now, again, I don't know what any of these words are on here, but I can see that this word and this word are the same. So that probably means number. This probably means, let's say, population number, sample number, and then this, I hope it means random, right? It's the type of sample that we want to get, a random sample. So let's pretend, is there a situation where you could know the truth? You really could know what the parameter is? I don't know how I found this, and it sounds made up, but there was this thing called the Phoebus cartel. And the Phoebus cartel was a bunch of guys who worked at light bulb companies. And light bulbs were getting better and better and better. And they realized that if we keep making light bulbs that last longer, no one's going to buy any light bulbs anymore. So we should get together and we should cap the amount of hours that a light bulb lasts. And so all the people who ran light bulb companies got together. I think this would be illegal, and said, hey, make your average light bulb last 1,000 hours. Now, I don't know if this would happen today. Anyone ever get the red ring of death on their Xbox or anyone's iPhone go out like the day after their warranty expires? This is called technological obsolescence. And look, they even advertised, we guarantee that your light bulbs will last 1,000 hours, because they're manufactured specifically only to last 1,000. But we can think about what would happen if you took a sample of 10 light bulbs. What would you get for the mean? Would you get exactly 1,000? No, that would be a little weird, wouldn't it? You wouldn't get exactly 1,000. Maybe you get one light bulb that lasts 998, one that lasts 1,050, 4. You ever notice this? Like when the light bulbs in your bathroom go out, one of them will go out, and the next day the other one will go out. There's not a lot of variability between those. Maybe the next one lasts 990. You add all those up, and you get X bar equals, I don't know, let's say 992. Where did that number come from? It's random, right? It's just a random number. But if you spent the rest of your life going out, taking samples of size 10 and plotting out how long the average light bulb lasts, eventually you would get something around 1,000. Sometimes your mean would be a little bit higher. Sometimes your mean would be a little bit lower. Sometimes you'd get a great bunch of light bulbs way up here. Most of the time, on the average, they would be something around 1,000. And this is the next question that we have to answer is how spread out would these means be? What would be the spread of these means of size 10? This is a very important concept called the standard error. I can't spell. Standard error of the mean. And it's not error as in mistake. It's error meaning deviation or variability.